So let's recap basis and components once more. Basis, as you know, the minimal set of vectors to span that space, which will mean that the basis vectors are linearly independent. Otherwise, it won't be a minimal set. The moment you have a basis, any vector in that space can be expressed as a linear combination of these vectors in the basis set. That's the reason why these things are called the basis. In Rn, you have n components for all the vectors in Rn. Then you need n basis vectors too. If Ai, ith column of matrix A, is a basis vector, then you will need n of them. So once you have a basis, a vector is a unique linear combination of the basis vectors that we saw multiple times. Then let me introduce a new notation here. For any vector in Rn, suppose you have a basis of Ai, which are columns of a matrix A, then any vector x in Rn can be written as a linear combination of the columns of the matrix A, Ai. Those components, those scaling factors, are actually the components of the vector x in the basis of Ai. That's the definition of the components. If you can write the coefficients that specify the linear combination are the components of the vector in that basis. And that is this little notation that says xi bar A, the ith component of x in the basis A. A linear combination is unique, which means the components of the vector are unique also. The vector can be written only in one way, one unique linear combination. But what will happen is that when you change the basis from one set to another set, you will get different components. The best possible basis set that you can have is the identity matrix. If you have any vector at all, the moment I specify a vector, I'm already giving you the component. For instance, I specified a vector B here. What are those components? What basis do those components refer to? That is a fair question to ask. The answer is that they are based on the identity matrix. Suppose I have a vector in R2 and I have two components, 2 and 3. How can I even say that 2 and 3 are the components? Where do I get the numbers 2 and 3 from? What I'm saying is that it actually comes from the identity matrix. Identity matrix in R2 by 2 is 1, 0, 0, 1. And multiply that with my original vector x, I should get the original vector back. But we can also look at this multiplication here as a linear combination of the columns of the identity matrix. First column 1, 0, second column 0, 1. That is the column picture of matrix multiplication. So it is 2 of the first column plus 3 of the second column. Now if you look at this guy, 1, 0, that is a vector. That is a unit vector and it's got unit length. The second one also, the norm is 1. And more than that, take the dot product of those guys, that is 0. So they are orthogonal to each other and they have unit length. So that's the best possible basis that you can have. We will call this guy, say Q1, and the second one Q2. Those are the unit vectors, normalized and orthogonal vectors. And in physics, they are actually called I and J. Once you have this one here, 2 times Q1 plus 3 times Q2, that is a linear combination of Q1 and Q2. And that gives you the original vector 2, 3. And if you want, you can specify that that vector is in the basis I in 2 by 2. That is what the subscript means. So 2, 3, the components that I have for this vector actually come from the identity matrix, and you can explicitly state it by putting that subscript I if you want. But nobody does that. So it's a perfect basis. It's the best possible basis that you can have because the columns are unit vectors orthogonal to each other. They're orthonormal. So we can write that in one simple mathematical statement that says Qi transpose Qj, that means Qi dot Qj, is 1 when I is equal to j. So that is the orthogonality and normality conditions in just one statement. So these vectors are actually more than orthogonal. They are orthonormal. They are orthogonal to each other and they are also normalized. So the right word to use is orthonormal. There's one interesting fact that the dimension of the space is the number of basis vectors, which is also the same as the trace of the matrix. Trace is basically just a sum of the diagonal elements. This trace of the identity matrix, which is the basis of that space, will actually be the dimension because each column has just one in the diagonal element. So just add up, you'll get the number of columns or number of rows, same thing. And that is the dimension. People like to use the concept of trace because it's got interesting properties. Whenever they see trace anywhere, they get excited and they use it. Okay, so that is one very good basis set that we saw. and that basis set was actually orthonormal. But it's not just the identity matrix that is orthonormal. You can have other matrices also if you have the same property. If you have any two of them multiplying, first one transpose the second one is 1 when the numbers are the same, the indices are the same, and if they are 0 when the indices are different, then they are orthonormal. Orthonormality implies some interesting properties. It basically means that taking the inverse is just transposing the matrix Q1, Q2, Qn standing in columns. That is my Q matrix. My Q transpose in rows. And if I take the product Q transpose Q, Qij is actually, as an element, is actually Qi transpose as a vector and Qj. That comes from the dot product version of a matrix multiplication. Ith row of the first matrix dotted with the jth column of the second matrix. And we know that this is equal to 1 if I is equal to j and equal to 0 when I is not equal to j. So that means it's an identity matrix. And that is true only if this is equal to 1. If it is just orthogonal and not orthonormal, then the dot product will not be equal to 1 when the indices are the same, because the norm is not 1. Okay, so that's why this applies only to orthonormal, not orthogonal. But like I said, people use orthogonal to mean orthonormal. So when they say orthogonal, most of the time they actually mean orthonormal. So you will see the statement, the test for orthogonality of a matrix is this. That's why Q transpose or Q transpose Q is I. And that gives you test for orthonormality. An orthonormal matrix preserves the norm. That is the second statement. So that also you can see. What's the norm of Q times X? So basically Q is a matrix and X is a vector. So Q times X is a vector and Q is a square matrix. So it's kind of transforming the vector into a different vector in the same space. So it's taking X and giving you another vector in the same space. And the norm of that vector is the same as the original vector. That is what I'm saying here. So let's see why. The norm of Qx is the same as norm of x. That's what we need to prove. So norm of Qx is the dot product of Qx with itself. So that is Qx transpose Qx. And you can apply the product rule of transposes. So this guy becomes the product of the transposes, but in the reverse order. So X transpose, Q transpose, and you can think of Q transpose Q, which is equal to I from here. So you put I there, then that becomes X transpose X, which is the square of the norm of X. So the square of Qx norm is the same as the square of norm X. And as you know, norm is a positive, is the length, is a positive number. So you worry only about the positive square root. So you can say that the norm of Qx is the same as the norm of X. Then the other thing is orthonormal matrices all have unit determinants. By unit I mean plus or minus 1. So if we take the determinant, you know that the inverse is the same as the transpose, so the determinant of the inverse is the same as the determinant of the transpose. But from the properties of determinant, you know that the transpose of a matrix will have the same determinant as the original one, and the inverse of a matrix will have the reciprocal of the determinant. So this guy gives you 1 over determinant of Q, and this guy gives you just determinant of Q. What does that mean? It means determinant of Q squared is equal to 1. That means determinant of Q is 1. So the last two proofs are elegant because they're using matrix algebra, and that's the kind of proof I would like to see, because even though they might look trivial, they are real proofs. And the reason why the proofs work is because there is this whole machinery of linear algebra, the syntactical engine of linear algebra that we built up standing behind these little elegant expressions there. Let's move on to change of basis. Let me give you a motivation why we might want to do change of basis. It is used in computer games, in multiplayer games. If you have the world seen from your perspective as you're playing it, and you have somebody else playing, and the same world, same three-dimensional world that is in the computer memory is viewed from a different perspective, from somebody else's perspective. This change is actually a change of basis. It's actually more complicated than a change of basis, but fundamentally it's actually a change of basis. So how you compute that is what you have to figure out. So in order to do this, you have a vector typically given in the identity basis, the coordinate basis. Identity basis is also called the coordinate basis. So suppose I give you a vector, say 2, 3. If I don't say anything, that is in the identity basis. And I give you a bunch of basis vectors. Those vectors are also in the identity basis. So you can put them in a matrix, and that matrix then is in the identity basis. Then what I have is that the new components of the vector, based on the matrix of the basis vectors that I specify, the vectors are AI, standing in as column vectors in A, then that multiplying the linear combination is the same as the original vector. So that is a condition. So you have one vector, you have the components, and you have a new set of components and new set of basis vectors, and the linear combinations of the new basis vectors with the components should give you the same vector. That's why it's the components of the same vector. X is equal to A times a bunch of numbers that we call X sub A, because those are components in the basis matrix of A. That is very similar to AX equal to B. In fact, it's identical. This is A, this is X, and that is B. So it's A, X sub A is equal to X. And all you have to do to get X sub A, the components in the new basis, it's just A inverse times X. Since A is a basis matrix, it's a full rank invertible matrix. In the case of vector spaces, basis for vector spaces is a full rank and invertible matrix. So I can always take the inverse and just multiply. So it's actually a fairly simple thing to do. In fact, it's the same as solving the set of linear equations. A, X sub A is equal to X is a bunch of linear equations because I know X as numbers. I know A as a table of numbers. And X sub A, those are the only unknowns. So I just solve the set of equations. One way of solving is just multiplying by the inverse on both sides. Okay, so basis change is basically the same as solving a system of linear equations, and a myriad of ways in which you can do that. So change of basis. Let's take an example. In the coordinate basis, I have a vector, the green vector X, that reads 7, 5. So that means my unit vectors Q1 is 1, 0 and Q2 is 0, 1, the column vectors of the identity matrix. And I need to take 7 of Q1 to reach here. Then you add 5 of Q2 to reach here. Those are my components. X is 7 times Q1 plus 5 times Q2. So the components of X in the identity basis or the coordinate basis is 7, 5. Now suppose I change the basis to a different set of vectors, A1 prime and A2 prime. I have 3.5 and 2.5. What do you think the components of X are in this basis? How many A1 prime do I need to get to the tip of X, and how many A2 prime do I need to get to the tip of X? It's 2 and 2. So it's basically 2 times A1 prime plus 2 times A2 prime, which means in that basis, A prime basis, the components now are 2 and 2. Now let's take a complicated one. This was easy because A1 prime was a scale version of A1 and A2 prime was a scale version of Q2, scale versions of the unit vectors. Now A1 double prime is 2, 1, A2 double prime is 1, 1. So some vectors, and I have to express X as a linear combination of these two, which is possible because clearly A1 double prime is not linearly dependent on A2 double prime. How do I know that these two, they're not collinear, they're not on top of each other? So there will be some unique linear combination that will actually give me that. Let's try to find it. So I'm saying that what I'll do is I'll just look at the lines there. I'll see that if I take 2 A1 double prime, then add A2 double prime, 3 of them, then I'll get to the tip of X. So just by looking at that, I can say that the linear combination that I need is 2 and 3. So X in the basis of A double prime, a matrix that contains A1 double prime and A2 double prime as columns, is actually 3, 2. So let me summarize this. My original matrix A, which was the identity matrix, that was my original basis matrix, 1, 0, 0, 1. My Q1 was the first column, 1, 0, Q2, 0, 1. And my vector was a linear combination, taking 7 of Q1, 5 of Q2. So I get the vector components 7 and 5. Now I took a different basis matrix A prime, 3.5, 0, 0, 2.5. Then we saw that you needed 2 of A1 prime and 2 of A2 prime. So the components are 2 and 2. And the third case, I had a more complicated, not orthogonal this time. I have A1 double prime 2, 1, A2 double prime 1, 1. And we saw that this is the right linear combination that I needed, and that is unique. Every linear combination is unique. So that actually corresponds to a situation where you have a unique set of solutions, which is true when you have a full rank square matrix. So we saw that the components were 3 and 2. Now how do I get this? Now one thing you might want to notice is that when going from Q1 to A1 prime, the size of the vector increased. I'm scaling it up, and the size of the component actually decreased. So you can kind of see that there is some kind of reciprocal or inverse coming in somewhere. Let's try to do the third one once more, but I'll drop the double prime superscript so that it's easier to write. So what we have, the formula for change of basis is that the linear combinations of the columns of A with the new components in the new basis should give me the original vector, which means the components in the new basis are equal to the inverse of the basis matrix times original vector. And X sub A components of x in the basis of A, those are the only unknowns we can solve. X is specified in the coordinate basis 7, 5, and the basis matrix A also is specified in the identity basis because 2, 1, the first basis vector was in the identity basis, second one also is in the identity basis. Now my statement was that the new set of components will come from the inverse times, so I just have to find the inverse of this guy and multiply this on the right. That's all I need to do. What's the inverse of a 2 by 2 matrix? Swap diagonals. So in the place of 2, I get the other one 1. So 2 and 1, they just get swapped. And off diagonals, I just switch the sign. And then I have to divide by the determinant of A. Happily for us, it is 2 times 1 minus 1 times 1. So it is 1. That has the inverse. And the new basis is just the inverse times the original components. And if you do the multiplication, you get the components. Okay, now what I have are two linearly independent vectors in R3. Their span is a 2D subspace. It's a plane going through the origin in 3 dimensions in R3. So the vectors that I start from, A1 and A2, so if I arrange them in a matrix A, I have 2, 1, 1 and 1, 1, 0. So this is the basis matrix. It's not a square matrix now because I have only 2 basis vectors because my subspace has dimension 2 in R3. Now I'm constructing a new vector x by taking 2 of A1 and 3 of A2. So I know that the components will have to be 2 and 3. I'm actually doing this by construction. That's my vector x. Now what are my components in the basis for the subspace? To begin with, how many components will be there? I have only 2 basis vectors because it's a subspace, and I have to scale. I have to find the right linear combination of these 2 vectors. So there are only 2 components. So even though my vector that I'm starting from is a 3 component vector, the components in the new basis are going to be only 2 of them in number. That is because the subspace is defined by 2 basis vectors, not 3. So if I take 2 of the first vector and 3 of the second vector, I uniquely get the original vector, and that's all I need. So that is an important point to remember. Even though the x that you're starting from has 3 components, as a member of the subspace, I need only 2 numbers to specify it. And if it was actually a subspace that is a line, then there's only 1 vector in the line specifying the subspace. I need to specify only how much I need to scale that vector by. There's only 1 number that I need to specify in that. So let's try to compute the components in the subspace. So we'll start from the same set of equations. This still holds. Some linear combination of the columns of A will give me the original x vector. So I should have been able to write this way, but A now is not a square matrix, so I cannot really talk about A inverse. So that doesn't work. So that's why that is grayed out. So A is a tall matrix, but it's always full rank tall matrix. All the columns are linearly independent. How do I know that the columns of A are linearly independent? The columns of A are the basis vectors, and basis vectors are supposed to be linearly independent. So it has a left inverse. So I can find a matrix multiplying on the left that will give me the identity matrix. If I can find it, then I can multiply this equation here on both sides with A inverse left. So then I'll get the components of x in the basis of A as A inverse left times x. So the only question is, can I find A inverse left? Just to recap how we found the left inverse, I have A m greater than n. M is 3, n is 2. A transpose is going to be in R n times m. But A transpose A, so we'll get rid of these guys, and this is going to be in R n n, and that's a smaller matrix. N is smaller than m. This is a 2 by 2 matrix, and the rank, 2 columns are linearly independent, so the rank is actually 2. So A transpose A is a full rank matrix. So the moment I have an inverse, I can write the inverse condition so that the inverse of A transpose A multiplying A transpose A either on the left or right should give me I. Now I choose to multiply on the left so that I can extract the green part of it. That looks like something multiplying A on the left, giving me I. So that is the left inverse. It is probably kind of hard to memorize that left inverse is this, right inverse is that, etc. But if you know where it comes from, you can immediately write this guy. This is very easy to remember. This is always true. And then you can actually kind of derive left inverse in about 10 seconds. So this is the way I would remember it. Now let's actually do this computation. So I have A1 and A2 there, and my A matrix there, 2, 1, 1, which is A1, 1, 1, 0, which is A2, and my linear combination that I built by hand, 2 of A1 and 3 of A2. Now I want to compute the components, and for that I will compute the left inverse. So I'll compute A transpose, then multiply by A, take its inverse, and then multiply that by A transpose. Tedious computation. I cannot get this right in a million years if I try to do this by hand. So I just did it in Sage Math. So it gave me the answer. That's the answer. The left inverse times the original vector x will give me the components. That turns out to be 2, 3. We started with 2a1 plus 3a2 and we retrieved it using our left inverse. So that method actually works.